Okay, so in this video we're going to do some review problems for an exam for a statistics class. Generally dealing with the binomial distribution, normal distribution, some amount of discrete distributions and continuous distributions mixed in with that, and then also confidence intervals. Okay, so first question, we have a discrete distribution with the following probabilities. Probability that we get a 3, x is 3 is 0.34. Probably x is 5 should be 0.25, 9, 0.32, 12.09. Now we want to find the mean of the distribution. So we're just trying to figure out how discrete distributions work. One of the ways you can do this is sort of do this by hand, here sort of directly. And our mean, it's going to be mu. It's going to be a sum of x times the probability of x. You add up this for every possible x. So in our case, it's going to be 3 multiplied by 0.34. So it'd be with the x equals 3. That's x, or x is 3, probability of getting a 3, plus the 5 times 0.25, plus the 9 times 0.32, plus the 12 times 0.09. And you're just going to calculate that, and I'm going to use my calculator to do that. So 3 times 0.34 plus 5 times 0.25, whoops, not times, but plus 9 times 0.32 plus 12 times 0.09, and this spits out an answer 6.23. And kind of to check if that's at all reasonable, I should figure out, well, 6 kind of in the middle of these values should be weighted a little bit lower because these 3 and 5 has a higher probability than the 9 and 12, and it seems okay, sort of plausible here. Okay, so my answer is 6.23. What I'm going to do is go through this whole page sort of by hand, and then I'm going to go back and use sort of a calculator. There's a function that sort of just spit out the mean for you, so you don't have to sort of do this calculation. Okay, next bit, we want to find the variance of the distribution. So the variance, that's sigma squared. The formula is I add up, I do x minus mu squared times the probability of x. So mu, if you use the 6.23 from part A, so for 3, I'm going to get 3 minus 6.23 squared times the probability of getting a 3, that's 0.34. Plus for the 5, I get 5 minus 6.23 squared times probability of getting 5 is 0.25. Just going to go down here, plus for the 9, I get 9 minus 6.23 squared, times the probability of getting a 9, that's 0.32, plus 12 minus 6.23, and just square that, times the 0.09. So I put these all together. I'm definitely going to use my calculator to do this. 3 minus, 6.23 squared times 0.34 plus 5 minus 6.23 squared times 0.25 plus 9 minus 6.23 squared times 0.32 plus 12 minus 6.23 squared times 0.09. So I just run that calculation. I get 9.3771. So 9.3771 there. So again, I mean, it's a formula. I go through, I use this, I just calculate this out. Next one, standard deviation. So this is always the case that standard deviation, that's sigma, and so this is going to be the square root of sigma squared. So instead of going through this big variance calculation again, I just take the square root of the 9.3771, so square root of 9.3771, and this I'm going to have to approximate. So I'm going to do second square root. I'm just going to hit second and then the answer here. That'll bring up 9.3771 because it's the last thing I have as an entry. Or I could type out 9.3771 myself. And I get something like 3.062 maybe. 3.062. So there's my standard deviation. Last bit here, we want to find the expected value. Well, the expected value sort of this x, really this is just the mean. So just another word for the mean, what you sort of expect to get on average, and that's just the 6.23. So I'm just going to copy the result from part A. That's 6.23. Okay, so that was sort of, how to go through these questions sort of directly if you didn't have sort of the statistics calculator. But it turns out we can use the calculator to do this as well. So what I'm going to do is pull up my calculator. I'm going to enter in my x's and my probability of x. So to do that, I'm going to go to Stat, go to Edit, go to my list. Into L1, or one of the lists at least, I'm going to put my x's. I'm going to do 3, 5, 9, 12. And then into L2, I'm going to put the probability here. So I got a 0.34. First entry is going to match with the 3, 0.25, and the 0.32, and the 0.09 here. Now what I can do, I'm going to quit out of this. So L1 is the x's. I'll write that down here. So this one here, these ones are L1. L2 has the probabilities. And so my calculator, now I'm going to go to Stat, Calc. I'm going to do one variable stats. And I want to do this on L1, but then I do comma L2 to sort of use the L2 probabilities. So I hit enter and it spits out various things. What you'll notice here, it has the sum of the x bars, that's the x bar, which is really, okay, it's viewing this as a sample in that case, but the notation, it's the same thing for a mean. That's mu, that's 6.23. Get sum of x's, sum of x squared, sometimes you use that. Note we have a sample standard deviation is missing. That's because when you have a distribution, they're really viewing it as a population. So there really is no sample standard deviation. Just the standard deviation, 3.0622. We scroll down here, 3.0622. That sort of matches what we have here. This expected values, again, the mean matches. Note this n equals 1. What that's doing here is effectively adding these probabilities, which should add up to 1 for a probability distribution. So if you don't get a 1 there, and you're doing a probability distribution this way, there's other things you can do where you might have like 6 of these and 3 of these and 2 of those or something. But if you have a probability distribution, that n should always be 1. If it's not, it tells you either you didn't actually start the distribution or maybe you entered something in. Okay, next question. Okay, this says a multiple choice exam has 5 options per answer. There are 30 questions, and you decide to guess randomly. So this is a binomial distribution. So this is binomial. So we have binomial. So we have a bunch of trials. We have 30 trials. Write out very well. So we have 30 trials. So each question is a trial. And our probability of success, that's P. Well, we have 5 options. So if you just guess, P is 1/5, or that's 0.2 as a decimal here. And then Q is the probability of failure. That's 1 minus P. That's going to be 0.8 or 4/5. Clean up that fifth there. There we go. Okay. So that's just our general setup. We have a binomial, and then we have to answer some questions. What is the expected number of correct answers? So this one, I think you can maybe just think through. But for a binomial distribution, this is really the average or the expected value. It turns out to be n times P. The idea is if I have 30 questions, and I have a 1 in 5 shot of getting each one correct, well, I should get about 1/5 of them correct if I guess. That'd be 30 times 1/5. That's going to be a 6. So 30 times 1/5. This is 30 times 1/5, or 30 times 0.2. This is the same thing as 30 divided by 5. I expect to get about 6 right on average. Now, of course, do this. I'm going to get sometimes 7, sometimes 8, sometimes 5, sometimes 3. So varied around here. Standard deviation. So what is the standard deviation? This one you can't really think of here. You just have to use the formula. And for a binomial distribution, the standard deviation is the square root of n times p times q. So for this particular example, n is 30, p is 0.2, q is 0.8. So you just go and calculate this. So we do a square root of 30 times 0.2 times 0.8, and we get like 2.19 maybe. That rounds to 2.19. That's really our standard deviation. I suppose you could actually calculate that if you did the binomial or the discrete distribution we did on number 1, but you'd have 31 options, that is getting 0 successes, 1 success, 2 successes, up to 30. So in principle you could do that, but it'd be a complete mess. This formula is really what you want to use here. Okay, sorry, part C. Find the probability you get fewer than 10 questions correct. So fewer than 10, I'm going to find the probability. Let's use k for the number of successes. I'm going to get the probability that k is less than 10. Now, that means I could get 0 or 1 or 2 or 3 up to 9. What I'm going to use is the binomial CDF function of my calculator. That always works with a less than equal here. So this is going to be probability that the number of successes is less than equal to 9. So less than 10, same thing as less than equal to 9. And I always want a less than equal just to match the calculator technology. If you have a different technology, then you might have to do something different here. And so what we get, this is going to be binom CDF. The way this works is it's really n, so that's the number of trials, 30. Probability of success, the p, that was 0.2. And then we put in this 9 here. So I'm going to go to my calculator, and that's just going to spit out some kind of answer. So what I'm going to do is go to second, hit the variables for the distribution, and I think it's toward the bottom, option B here, is binom CDF. 30 trials, probability of success is 0.2, and I'm looking for up to 9 successes. Sometimes if you've got a little bit different operating system on these calculators, you get kind of more of a menu setup. Hopefully you can figure out which ones go where there. I think it's probably in the same order, but I'm not entirely sure actually. So I calculate this, and what I get is, 0.9389. So 0.9389, something like that. So pretty good chance that you don't get 10 or more. You get fewer than 10 correct. Note here, we expected 6, so sort of half of the time, at least we should get 6 or fewer here. So we should have known what it's going to be bigger than 50%. Okay, now here's the question. Find the probability you get more than 8 questions correct. So this is the probability k is greater than 8. Now this is going to be 1 minus the probability that k is less than equal to something. And a lot of times I like to sort of draw a little bit of a picture. So I have 0, 1, 2, up to, let's say, 7, 8, 9, 10 successes, and then that would go up to 30. So I want to find the probability that I get more than 8 correct. So that's going to go 9. 8 is not more than 8. 9 is more than 8. So I want this sort of block here. And so what I'm missing from the whole thing is this orange block here. And so what I get is the last one in that orange block. That's my 8. There, so I'm looking for the 1 minus the probability that I get less than equal to 8 successes. And then I need to convert that into binom CDF language to do the calculation. So this is 1 minus binom CDF. Let's see, we have 30 trials, probability of success is 0.2, and now we're going up to 8. And so we can go here, we can do 1 minus second distribution. Go find binom CDF. 30 trials, 0.2 probability of success, we're going up to 8, and this should spit out an answer, and we get, I suppose it's approximately 0.128, and that 6 would round to a 7. So 0.1287, if I go to 4 decimal places. Okay, next one, find the probability that you get exactly 5 questions correct. Well, exactly 5, that's really the probability k equals 5. So I'm not going to use the binom CDF. When I have an equals, I can use the binom, and then it's PDF here. So I have 30 trials, probability of success is 0.2, and I expect to get 5, and then I'm going to get an approximate answer, most likely. Sometimes I'll get a decimal that is actually to a small enough number of places where I can put all of them. So binom PDF. 30, probability of success is 0.2, looking for exactly 5, something like 0.1723, if that last second 2 would round to a 3. So I get 0.1723. So there's my answer there. Okay, last one of these, find the probability you get between 3 and 7. So I'm going to draw another one of these pictures like we did up here. So between 3 and 7, So I could get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 up to 30. So what I want between 3 and 7 inclusive, I want this block here. So what I'm going to do is I'm going to take a big block up to 7. I'm going to take sort of this orange part, and then I'm going to subtract off, let's pick, how about a purpley thing here. I'm going to subtract off this sort of block from 0, 1, 2. So that'll leave me with the blue. I take the orange minus the pink, gives me the blue. So what I'm going to get here is I'm going to get binom CDF. This will be the orange. 30 trials, probably success is 0.2. I'm going to go up to 7. So that's probably getting 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7. And then I have to subtract off this 0, 1, 2 bit. So that's a binom CDF. 30 trials, probably success is 0.2. 0.2. And I'm looking for up to 2 successes to subtract off because the last thing I don't want is the 2. So I run those here. Let's go here. So let's do second distribution. Binom, whoops. I wanted the binom CDF. Get PDF. Binom PDF. 30 trials. Probably the success is 0.2 up to 7. Minus another binom CDF. 30 trials. Probably success 0.2. This time we're going up to 2. And spits out 7166. So 0.7166. So about 71% of the time. Let me clean those up a little bit, those 6s here. About 71, 72% of the time, you should get between 3 and 7 correct. Note, 6 was the average, so we're including sort of the high parts here. Okay, next one. So this says 17% of American children have blue eyes. You randomly select 20 American children. And then we've got some questions here. So again, we're going to assume this is a binomial distribution. I suppose technically we should be doing this with replacement, but the number of American children where if I pull one out, and that child happens to have blue eyes, I suppose this probability would change slightly, but that probability is rounded anyway, and it's not going to change enough to matter. So we're going to view this as a binomial here. So this is binomial. Number of trials, that's our n. Here, well, there's 20 children, so that's 20 trials. Probability of success is 0.17, which means Q, or probability of failure, is 1 minus 0.17. That's 0.83. So this is a binomial. So that's the identification. And then the actual question, was it probably that exactly 4 of the children have blue eyes? Well, then that's just a binom PDF. We have 20 trials. Probability of success is 0.17. And we're looking for exactly 4. There's a formula you could use here as well, but I'm just going to use the binomial PDF. Second distribution. Binomial PDF, 20 trials, probability of success is 0.17. Looking for exactly 4 successes. So we get 0.205, and that 2 would round to a 3. 2053. And I like to put the approximately 0.2053. So there we go. Next one was probably that more than 2 of the children have blue eyes. So let's see, we have 0, 1, 2, 3, 4, up to 20. So more than 2 is the block from 3 up to 20. So what we're going to do is really take the whole thing, that's 1, minus the block from 0 up to 2. So what I'm going to get is the probability of getting anywhere from 0 to 20 is 1, minus this block in orange. That's going to be a binom CDF. Probably, we have 20 trials. Probably the success was 0.17, and we're going up to 2. So that works out to be 1 minus second distribution, binom CDF. We have 20 trials. Probability of success is 0.17. Up to 2 trials, up to 2 successes, you get 0.6854. Not a very good 8 there. Better. So our probability is something like 0.6854 more than 2 of the children have blue eyes. I have 20. Pretty good odds. Okay, what is probably that between 5 and 12 have blue eyes? I did one like this before. Oops. What I'm going to think about is I have 0, 1, 2, 3, 4, 5. I'm just going to write all this out. 7, 8, 9, 10, 11, 12, 13, 14, and then I'm going to go down to 20. What I'm looking for is the amount probably going to be between 5 and 12 here. So again, what we're going to do is take the whole thing down to 12. And that's because our binomial CDF only does a less than equal, so it can only start at 0, add all these up, and go to 12. And then I'm going to subtract off the bit from 0 to 4. And so what I get here is going to be binomial CDF for the orange part, 20 trials. Probably a success was the 0.17, going up to 12. And then I need to subtract off sort of this purpley part. I get binomial CDF, 20 trials, probably success is 0.17. We go up to 4. And so what you get is second distribution. Whoops. Binomial CDF. 20 trials, probably success is 0.17. We're looking for 12 for the first bit. Minus, overshot it again. I get a binomial CDF, make sure they're both C's. 20 trials, probably success is 0.17, and I go up to 4. Hit enter, and I get like 0.2443. So that's your answer. I feel like here I'm just going to add sort of an additional thing. There's a, let's see, let me go find it. So there's a more advanced calculator you can get called the, called a TI Inspire. So I'm just going to load this up quick here. I'm going to admit to not being terribly familiar with the menus, but they'll have a binomial CDF as well. They just have a little bit different function here. So this isn't something you need, but if you've got one of these or if you've seen them, there's something nice you can do here. So we're going to let this load up. Or maybe we're not. Maybe I won't load up here. Oh, nope, there's going to go. Okay, so here's this calculator. I'm going to do my calculator. And here's sort of what this calculator looks like. It's a little bit different here. So what I can do, let's see, I believe I can go to menu. And then I'm just going to go over here, but it's like using the sort of the big screen here. I can go to statistics, presumably distributions. And I have these particular things here, and I have a binomial CDF. So same kind of setup. Now this one, I could do number of trials was 20. So 20 trials. Probability of success was 0.17. I'm going to do a down arrow. Lower bound. Now let's see what we do here. When we go back here, we're going somewhere between 5 and 12. And so what we get is our lower bound is 5. What's new about this technology is that the TI-84 always has a lower bound of 0. But with this Inspire, I can go from 5 to 12, and then I hit OK. And I enter that, and it gets me the 0.244316, which matches the number we got here. So I just wanted to do that just so you could see there's some technologies that can do this in one shot, so you don't do the difference of these binomials. Obviously a little bit nicer, but it's nice to know kind of how to do this. Sort of as a subtraction. Anyway. Okay, so that's sort of an add-on thing. Next bit. So this says a random variable has a normal distribution with mean 37 and standard deviation 9.2. We know what is the probability the random variable has a value less than 30. Okay, so again, we can do this sort of by hand here. So what we can do, if we want to do this by hand, we want to convert our sort of scores to z-scores. So what we've got here, this mean, the mean is 37. So this is mu is 37. Standard deviation, that sigma is 9.2. Now this 30, that's an x. So x equals 30. And there's a relationship between z-scores, which is sort of the standard normal distribution, and the x. What you do is you do z is x minus mu over sigma. So in our case, that would be 30 minus the mean is 37 divided by 9.2. So we get a negative 7 over 9.2. So what you're saying here is we're distance 7 below the mean, and we're going to figure out basically how many standard deviations below the mean that is. So 7 divided by 9.2 will give me the number of standard deviations. I do negative 7 divided by 9.2. The negative signifies I'm below the mean. So this is something like negative 0.76. So negative 0.76. Then, once I have that, I can look up in a table here. So here's our standard normal table. And what I'm looking for is just the negative 0.76, and then I get a probability that I'm less than that value. So here's negatives. Negative 0.7. This is 70, 71, 72, 73, 74, 75, 76. So it's this 0.2236 here. So that's our value. So you can do this way, and it's, gets us, our probability is 0.2236. Let's make sure remember that right. Okay, so that's really your answer. So that's one way you can do this all by hand if you didn't have the calculator. Now with the calculator, probably the right thing to do, the simplest thing to do, I'll write this in a different color, here, let's do green, is I can just go say, let's do normal CDF, and then I give a range. So less than 30, now this is a bit strange, I have to go from negative something really low, so like negative 999 up to 30, and I have a mean of 37, standard deviation 9.2. So I'm going to calculate that. Note here, couple things. The less than 30, I don't have to go to 29 because normal distributions are continuous. So instead of doing a 29, it's really like 29.999999 here. So it's effectively 30. There's something about calculus where you can really say 30. So for a continuous distribution, less than 30 is the same thing as less than or equal to 30 in terms of probabilities. For the discrete distribution, that was not the case. I would go from 30 down to 29, but here I can do 30. And then the negative 999, I just need something that's far enough from the mean that's enough standard deviations, like probably 5 or 6. Probably get away with 0 here. It'd be about 4 standard deviations. Maybe that would matter, but something really negative. So effectively, I'd like to put a negative infinity here, but I can't with the technology. So I go second distribution, normal CDF, and I'm just going to do negative 999, comma, 30, comma, 37, and then the standard deviation is 9.2. Close that up, and I get 0.2234 here. Note there's a slight difference between the answer from the table and here. That's coming about because we rounded this negative 7 over 9.2 here, and that's sort of as precise as our table was. So really, this negative 70 by 9.2 is negative 0.760. That's between negative 0.76 and negative 0.77. So if you went to the table, so this was 0.776, 0.77, or no, it's negative 0.77. So I should get an answer between 0.2206 and 2236. And we can see we got that there. It's closer to the 2236. And it's because we've got like a negative 0.761. It's really a lot closer to 0.76, or negative 0.76. Anyway, what we get is 0.2234. So either of these answers are okay, as long as you sort of justify them appropriately here. Okay, so 2 routes here. Let's do both of these again for B. So for B, let's use the normal CDF. What is the probability the random variable has a value larger than 35? So what I'm going to do here, this is normal CDF. Now larger than 35 means I start at 35 and I go up to, say, 999. And then mean is 37, standard deviation is 9.2. And so what I'm going to do, I like to hit second enter here. Oops. Yep, there we go. And I can just type in what I have, 37 up to, no, sorry, not 37, 35, comma, 999. I can delete that, although I could do 9990, that would have been fine. And I get something like 0.5860. So 0.5860. Yeah, I suppose that's not technically equal, that's approximately equal. So I should have fixed those up here too. Here, and I suppose while I'm at it, negative 7 over 9.2 is approximately negative 0.76. Okay, so other method using the table, what you could do is your z-score here, again it's x minus mu over sigma, x here is 35. Mu is still 37 over 9.2. So that's negative 2 over 9.2, which is approximately, it's going to be, let's see, negative 0.22. So I only really need to go to 2 decimal places because it's all my table has. So this is negative 0.22. And this leads to a p-value. Now, this one's going to be a little bit different because what I want, just draw my normal distribution here. So my z, let's see, this would be 0 here. So negative 0.22 is over here somewhere. What I want is this area to the right. But what the table will give me when I look up negative 0.22 is only the area to the left. So the table gives me this area here. So what I'm going to do to calculate this is I'm going to do 1 minus sort of this orange area. So I can look up the orange area, and then this blue shaded part is 1 minus the orange. So you look up negative 0.22, negative 0.20, negative 0.21, negative 0.22, that's 0.4129. So 1 minus 0.4129, and that's going to be, if I do the subtraction, 1 minus 0.4129, so that to be 0.5871. Again, not quite the same, but there's a little bit of difference in the rounding here. The calculator is actually going to be more accurate here, because essentially it's got a much more detailed table. Okay, now what is the probability the random variable has a value between 32 and 40? If I use the normal CDF method, which is probably what I would actually do, all I do is say, oh, I'm between 32 and 40. I don't have to mess around with this 999 or negative 999 business. I just do go from 32 to 40, mean 37, standard deviation 9.2. And I just go second distribution, normal CDF, 32 to 40, mean 37, standard deviation 9.2, and I hit enter and I get 0.3344. 0.3344. So there's my answer. Now if I wanted to do the z's, I'm actually going to get 2 z-scores. So what I'm going to get in my picture here is I'm going to get, let's see, the mean, so 37 is really the 0. 32 is going to be somewhere here to the left. That's distance 5 below the mean. Well, 5 in the x. And then 40 is going to be somewhere over here. And I'm going to try and find, I have to figure out those values, I'm trying to find the area in the middle here. So that's really our setup. So let's try and find the z-scores here. I have to use the z-scores because I only have a table for the standard normal distribution. And so the z, let's see, with the, let's do the x is 32 first. So I get 32 minus 37 over 9.2. That's negative 5 over 9.2. Which again, let's say I only need 2 decimal places. Whoops. Negative 5 divided by 9.2. Negative 0.54. So this left bit on the diagram is negative 0.54. And my other z is the 40 minus 37 over 9.2. That's 3 over 9.2. Something like a third about, I would appear to be. And I get 0.33 it would round to, and again I only want 2 digits of precision because that's all my table has. And so this gives me 0.33. So what I'm going to do now is I'm going to do sort of 2 parts here. First part, I'm going to get sort of this orange. I'm going to add up to the 0.33, and then I'm going to subtract off sort of this pink part that's to the left of 0.54. So what I'm going to do, I'm going to look up the orange. I get the whole left tail up to 0.33. Again, I have to sort of start from the far left because that's what's in my table. So let's look up 0.33. It's actually going to be on the next page here. So I get 0.30, 0.31, 0.32, 0.33. I get 0.6293. So what I get here, the orange, let's do that, 0.6293, and I have to subtract off that pink part here, or purple, or whatever color that is. So I'm looking up negative 0.54. Whoops. There. Negative 0.54. negative 0.50, negative 0.51, 52, 53, 54. So it's the 0.2946. So minus 0.2946. And so what I get, let's do 0.6293 minus 0.2946. I get 0.3347. So my answer here is it's approximately 0.3347 here. Kind of ugly 4 there. So 0.00347. So these values, again, pretty close, not quite the same, and so the rounding's not as bad in this one. Next one. What score represents the 36th percentile? So first off, we're going to do the calculator method, which is probably what I would do. What I can do is I can just do an invert norm. I want the 36th percentile, so I put in 0.36. And then I do the mean and then the standard deviation. So mean was 37, standard deviation is 9.2, and this will just spit out my answer. So I do second distribution invert norm, 0.36. I'm looking for the 36th percentile. Mean is 37, standard deviation is 9.2. Spit out 33.70. That's really our 36th percentile. With the sort of book method or without the invert norm functionality, what I would do is I would take my standard normal distribution. I've got my 0 there. I'm looking for some part here where what I get is in there I get 36%. So I want to try and just find that cutoff where sort of the shaded part here is 36% of the data to the left, and that'll be the 36th percentile. Now that'll be a z-score, which I'll have to convert to x here. But what I'm going to do is look at my table. I'm looking for 0.36 here. So 0.37, 0.3, here we go. So it's between these two. So this is negative 0.30, 31, 32, 33, 34, 35, and 36. So I'm going to look at this. It looks closer to the 36, so I'm going to pick the negative 0.36 here. You know, there's some error there, but that's what we'll live with. So this is negative 0.36. Now, this is just random. Wow, that's actually kind of interesting that the 0.36 matches the 36%. That's generally not going to happen here, but it worked out in this case. So it's not negative 0.36 because it's 36%. It happens that if I look at the table there, what I get is that that's negative 0.36. Sort of that's my cutoff to when I get below 0.36. So if we had like 0.2, say, as we went 20% to the left, that'd be here and here, and we get negative 0.8, 0, 1, 2, 3, 4, maybe negative 0.84. So the fact that this worked out to be 0.36 and 36% is 0.36, that's just happenstance here. Okay, so once we get that, that's really our z-score. So z is negative 0.36. And our formula here is z, again, was x minus mu over sigma. So we want to solve this for x. So multiply both sides by sigma. You get z sigma equals x minus mu. And then you can add mu to both sides. And I get x is mu plus sigma z, or z sigma. So what I get, in this case, mu is 37. Sigma was 9.2. And then that z is the negative 0.36. And so that works out to be, let's see, 37, so it's going to be plus 9.2 times negative 0.36. Works out to be 33.69, maybe. So that would be an acceptable answer as well, sort of working this out by hand. So very similar results. Okay. Next one. Between what values does the middle 40% lie? Well, in our picture, if you do the middle 40%, I want to get this and have 40% in the middle. Well, that leaves 60% for the two sort of tails. 60 divided by 2 is 30, so you really should get 30% on the right and 30% on the left here. So I'm just going to start using the calculator. So what I want here, between what values does the middle 30% lie? Well, this first one, this should be, I have 30% to the left. So that's going to be second distribution. Let's write it down first. It's going to be invert norm. I need 30%. And then mean is 37. Standard deviation is 9.2. So I get invert norm. mean, or no, looking for 0.3, and I'm looking mean 37, standard deviation 9.2, and what I get is like 32.18. So that's sort of the lower bound for the middle 40%. This upper bound, we want to think how much is to the left? Well, 30% plus 40%, so that's 70% to the left. So this is invert norm of 0.7, 37, 9.2. And what that is, let's do second entry. Just change that 3 to a 7, 0.3 to 0.7, and I get 41.82. So here the middle 40% is between 32.18 and 41.82. Now it should be, when this is the middle 40%, that if you averaged those two, you should get the mean of 37. So what you could do, let's do it this way. How about 41.82 minus 37 would be the distance sort of from the mean to this cutoff. That's 4.82. If you did 37 minus 32.18, I should get the same thing. There's my 4.82. So sort of my mean is 37 and same distance to both sides. Do I actually get 40% here? This is just a check. Well, I could do a normal CDF, go from 32.18 up to 41.82. Mean is 37, standard deviation is 9.2, and I get, basically 40%. Okay, last one on this set here. What is the smallest value in the top 15%? So what we've got here is we want sort of 15% here. We're really trying to find the part here, which is, the percentile, which is the 85th percentile. So what we're going to get is this is just an invert norm, because if there's 15% in the top, there's 85% below. So invert norm is 0.85, 37, 9.2, and that's going to work out to be invert norm 0.85, 37, 9.2, and that's going to be 46.54. That should be the smallest value where there's 15% of all the values above that. So 15% of the time we should get something bigger than that. Okay, next one. It says a distribution has a mean of 126 and deviation of 15. What is the mean of the sampling distribution for samples of size 35? So because our samples are size 30 or bigger, the central limit theorem is basically going to apply. We're going to assume our sampling distribution is essentially a normal distribution. So what we get is a normal distribution with mean of the sampling distribution, that's mu x bar, is going to be the same as the mean of the original distribution. So the mean of the sampling distribution is same as mean of the original, which is 126. So short and sweet. Standard deviation of the sampling distribution, that's sigma of x bar. The formula is this is sigma of the original standard deviation of the original distribution divided by square root of the sample size, that's our 35. So we get is the 15 divided by square root of 35, which, let's change that to a decimal. 15 divided by square root 35, we get like 2.54. So our standard deviation shrinks from 15 to 2.54. Okay, now if we have sample size 50, what we get is 15 now divided by square root of 50. It's the sigma of x bar. This is our standard error, really. This should approximately 15 over square root of 50. I can just hit second enter, a little more efficient here. 50. And I get like 2.12. Or something like that. Okay. Next one. What is the probability that a sample of size 40 has sample mean less than 120? So we have a normal distribution. So I'm going to use normal CDF here. We want to go less than, sample mean less than 120. So that's negative 999 up to 120. The mean of the sampling distribution is the mean of the original distribution, which I forgot what it was, 126. Here. The standard deviation of the sampling distribution is going to be something like 15 over square root of the sample size. So it's 15 over square root of 40. I'll write that 15 a little bit nicer. Now there's a temptation to kind of convert this to a decimal. I would just put 15 over square root of 40 into my calculator. That'll make your result more accurate, and then you're not worried about writing the decimal down a couple times. And so I'm going to second distribution, normal CDF, go negative 999 up to 120. Mean is 126. Standard deviation is 15 divided by square root of 40. So what I get is something like 0.0057. So this is really fairly unlikely here. Less than, that's about a tenth or half of a percent maybe, or 0.6%, 0.6% here. And that sort of makes sense. We have a mean of 120, or sorry, mean of 126. 120 is a bit lower than that. And it's enough lower that's just pretty unlikely. That's sort of kind of not something we'd really expect to get. Not completely impossible, but sort of odd, about 1 in 200 times. Okay, so there's probably a sample of size 50 has a sample mean greater than 127. Same setup. Note 127 is pretty close to 126, so I'm going to expect sort of a higher probability here, but let's see. Got a bigger sample size, so maybe not. So this is a normal CDF. Now I'm going to go greater than 127. It goes from 127 up to, say, 999. Mean is 126, and now our standard deviation was the 15 of the original distribution, and we divide by the square root of 50. And what we get, so second distribution, normal CDF, 127 up to 999. We have a mean of 126. Our standard deviation is 15, with our standard error, 15 divided by square root of 50. So we get 0.3187. So it's, you know, a fairly plausible thing. About a third of the time that's going to happen. So something that's sort of realistic to occur. Last one. What is probably that a sample of size 30 has a sample mean between 125 and 127? Well, 126 is in the middle, so I expect this to be fairly common. But let's calculate it. So this is going to be normal CDF. We're going from 125 to 127. Our mean is 126. The standard error or standard deviation of the sampling distribution is the 15 standard deviation of the original distribution divided by square root of 30. And so what we get, normal CDF, 125 up to 127, mean of 126, standard deviation 15 divided by square root of 30 here, and I get like 0.2849, except that's going to round that 9 is going to round that 9 up to a 9, so it's going to be about 2850. So I get 0.2850. So I guess I should have boxed the previous one. So something like about 1 in 4, maybe a little bit higher than that chance here. Okay, next one. Okay, so these ones, we're not going to do any calculations, sort of short and sweet. It says the following are the graphs of, well, okay, I got a typo here. These are 4 normal distributions. I can count there's 4 with the same mean. So which graph has the largest standard deviation? So I've got the same mean here. I'm going to assume these all have the same scaling here. So standard deviation, here's things that are sort of squished together more have low standard deviation. Things that are sort of squished down here have a higher standard deviation. More spread out is higher standard deviation. So I look at these, and A looks like it's sort of the most spread out compared to D. Like this one drops down and sort of nothing there, but there's still a little bit of room here. So A is sort of the most spread out. So the largest standard deviation, that's A. Next one is the smallest standard deviation. That should be sort of the most squished together in the middle. That's going to be C, and it sort of reaches a little bit higher than B. We can go sort of from this middle. We're going to have 1, 2 tick marks there. Here's 1, 2, and we're already about at the bottom there. So C should have the smallest standard deviation. Things are squished closest together. Okay. Next one. Let x be a random variable with a normal distribution, which is the following is equal to probably 3 less than equal to x less than equal to 8. So setup here. We don't really know where 3 and 8 are. I'm going to pick some points. How about here 3, there 8. But they could both be like way down here, both be up here. They could be spread out. They could be in the middle. We don't have any sense of what the mean is or anything like that. But I'm just going to put these somewhere. And so what I'm looking for is really this area here. let's just go through what pictures we get. So let's do this first one. 1 minus probability x greater than or equal to 8. So x greater than or equal to 8 would be here. So let's just say this first one. I don't want to circle that as an answer. I just want to do that. So let's just write it up. 1 minus probability x greater than or equal to 8. The picture for that is we've got 8 over here, and I have x greater than or equal to 8 there. So the picture is all of this. So this is similar to this, but it's actually missing this part below 3. So A, that's not the answer. Next one, let's do the probability x less than or equal to 8 minus the probability x greater than or equal to 3. Well, let's see. So what we've got, let's write that out. Probability x less than or equal to 8 minus the probability x less than or equal to 3. So this is 8 and 3. So probability x less than or equal to 8, that would be this whole purple part here. And then we're going to subtract off this, well, it doesn't show up very well, about this orange part here, x less than or equal to 3. And what we're going to be left with is sort of this part here. And that's actually exactly what we're looking for. So we can see here that B works as our answer. In some sense, we're done. I mean, if you're confident of that, I'm going to go through and look at the other ones and see what they do. So let's look at C. Probably x is less than or equal to 8 minus probably x greater than or equal to 3. Well, that would be the purple less than or equal to 8, but then we'd subtract the area from 3 to 8. So what you'd get is sort of this left tail less than 3 minus the area of the right tail greater than 8. So that's not what we want here, at least not in general. Next one, probably x greater than or equal to 8. That's this right tail. And then we subtract off probably x less than or equal to 3. That's the left tail. So it's right tail minus left tail. That doesn't give us what we want. Last one, probably x greater than or equal to 8 minus probably x greater than or equal to 3. So this is a little bit intriguing. So I'm going to take this area here and subtract off these two combined. This here, if I think about this, is actually going to give me negative of the probability that 3 is less than equal to x less than or equal to 8. So that doesn't work. Okay, so now clever test-taking strategy time with this. What you could do, if you're not sure how to do this, is I don't know what the mean is, I don't know what the standard deviation is. Let's make something up. So let's put the mean as like 5 and the standard deviation as maybe 1. So what I could do is do distribution, normal CDF. I'm just going to make up some numbers, but I'm going from 3 to 8. Mean is 5, standard deviation is 1. The idea here is I should get the same number for all these. So that's a little bit high. Let's make that standard deviation bigger. So let's make the standard deviation, how about 2? And then I get 0.77453. So that's what I'm looking for. And now I could go through each of these. 1 minus the normal CDF, probability that I'm greater than 8. So that's 8 to 999. And we picked mean of 5, standard deviation of 2. And the idea here is if these two match for any distribution, I should get a 0.774. So I get something different, tells me 1, not the answer, or port A, not the answer. Next one, B, this is second distribution, normal CDF, less than or equal to 8, so that's negative 999, comma 8, mean of 5, standard deviation 2, minus second distribution, normal CDF. Let's see, we're going x less than or equal to 3, negative 999, comma 3, comma mean of 5, standard deviation 2. Again, I just sort of made up the 5 and 2, but I want to use those all throughout. I'm looking for 0.77453. And it went off, but you can off the screen, but you see I get the same answer. So I'm going to go through a couple times just so we can see. So this was the original thing. And you can see these are actually the same exactly, and that tells me B is correct. If you ran through the rest of these, like let's do E here, so you can see what I'm talking about with the negatives. So I get probably x greater than or equal to 8. So that's 8 to 999, comma 5, comma 2, minus normal CDF. We're going greater than or equal to 3, so that's 3 to 999, mean of 5, standard deviation of 2. And that gives me almost the same thing, but I get this negative out in front here. So that's actually not correct. And you could go through each of these and see they're different. So that's kind of the test-taking strategy. Maybe feels a little bit like cheating on it, but you can get the right answers. This is one of the downfalls of multiple choice questions is you sometimes get the answer without really knowing what you're supposed to know here. But yeah, that's okay. It's okay. I don't really think that, I mean, I should be clear, I really don't think that's cheating. It's just sort of using what you have at your disposal, sort of test-taking strategy. Okay, next one. Sample of size 50 has a sample mean of 925 and a sample standard deviation of 37. We're going to find a 90% confidence interval for the population mean. So what we're going to do is build our confidence interval. General setup here is our margin of error. Switch to the darker blue here. So our margin of error, it's going to be generally some critical value times the standard error. Here. Now, in this case, we have our standard deviation as a sample standard deviation. So we want to use a t distribution. So our critical value is like a t sub c. And then we're going to multiply this by a standard error. Well, that's going to be the standard deviation of the sampling distribution. So sample size 50, it's going to be s over square root n. So we get t sub c. We have a 90% confidence interval. So we look up t.9. I'm going to go to my table here. Oops, this is the t distribution table. What I can do is I have a 0.9 level of confidence, but I need to know, let's see, sample size is 50, so degree of freedom is 49. So I have degrees of freedom. I need to go to 49. I gotta make sure I'm in 90%. So this column here at the 1.771. This column here, we're still not at 50, so like the 1.706 there. And 1.706. Now we get to 50, that's really, so this degree of freedom is sample size minus 1. So we're really looking for a 49 here. So we probably should use the one that's a little bit bigger, 1.679. So that critical value is 1.679. Sample standard deviation is 37, and n is square root of 50. So again, if you use some other book, sometimes they'll say once you get bigger than 30, just use the z value. The z value is at the bottom, that's 1.645. That's going to introduce more error than you would get if you used the, what do we use, 1.679. Now, not a huge amount, those are pretty close together, but some error. So this 1.679 is actually better here. Okay, so you get this, your margin of error then is, let's see, 1.679 times 37 divided by square root of 50. Here is 8.79 maybe. Let's just say 8.8 here. Let's just leave it as 8.8. So that's our margin of error. And so then our actual confidence interval is what we're going to do is take our mean of 925. You're going to get 925 minus the margin of error. So mu is our population mean between that and between 925 plus the margin of error. So what we get is 925 minus 8.8 is 916.2. So we expect the mean 90% of the time to be between 916.2, and I can do second entry and change that minus to a plus. So it's 933.8. So that's really our answer there, and we kind of just work that out. Now a couple things here. One, this 1.679, if you've got the right kind of calculator, so I think like the TI-83s don't do this, but I can do a invert T. I can say I have a 90%, so what I'm looking for here, what I'm looking for is the middle 90% here, but that leaves 5% on each tail. So 10% between the two tails, 5% on each tail. So I'm really looking for this point here, which has 95% to the left. So that's a little bit confusing. So I do invert T 0.95, and then I have to put the degree of freedom, which is 50 minus 1, that's 49. So that gives me, thanks for a little bit, 1.677. Note this is different because we went to degree of freedom 45, or if you went to 45, you should get something that rounds to 1.679. So you can get a more precise answer there. Again, I believe the TI-83 or sometimes some versions of the 84 won't have that invert T. So you go to second distribution, you may be missing this invert T here. So you can't really do things that way. That's okay, because the way I would really do this on my calculator, and what I would probably write down, say, on an exam, if this is okay, is I'm going to go, and I'm going to go to stat, I'm going to go to test, and I have a T interval. So not the T test, but the T interval. So I go down to T interval. This is option 8 on this calculator. hit enter. I have to go to stats because I don't have a list of sort of the numbers. So this is from some calculation earlier, x bar, but in our case, our mean is 925. SX, now it's a t, so it gives you a sample standard deviation. That's 37. Sample size was 50. And our confidence level is 0.9. So just kind of put that in. Now what I would write down on the exam is sort of say, this is what I did in my calculator. If I put in t interval, say what function I used, x bar, I did 925, SX, I did 37, N, I did 50, and then C level, confidence level, I did 0.9. And this is sort of, you have a record of what you put in there. And if you do this and you go to calculate, hit enter, what I should spit out is this interval. So 916.23, 933.77. So up to some rounding, but actually it should be rounding to one less digit of precision in our answer. That actually works out the same. So you could do this and then get that answer, but then you want to put down, hey, here's what I did, instead of just writing the interval. Okay, so now if I want to find an 80% confidence interval for the population mean, what would change if I did this method here, that 1.679 would just get replaced with the 80% confidence interval. So this was the, so I gotta figure out where they are. So 90, I have to go 2 to the left, is 80. So at the 45, 1.679, it would get replaced with 1.301 here. So I get my margin of error. Let's go to the blue here, actually. Margin of error is 1.301 times 37 over square root of 50, which is something like, hit second enter, second enter, second enter. Might have been faster just type this in, but what I need to do is change that to 301. That's all I change, and I get like 6.8 here. So I have a margin of error that's like 2 smaller here. And so what I'm going to get is I have a distance 2 less in each direction. So I'm going to get 918.2 less than mu less than 931.8. So that works out. Or I just use t interval here, so I can do t interval here, and I'm going to put in x bar is 925, sx is 37, n is 50, and then my c level here is now 0.8. So I can do that, and then I want to write down the interval at the end, but I go second, oops, so stat test, t interval is option 8, so if I know that I can just hit 8. All I'm going to do is change this 0.9 to 0.8. Go to calculate, and I should get this interval out here, 918.2, 931.8. So there you go here. So really very similar here. You do these 200 out pretty quick. Next one. Okay, so it says a sample of size 40 is drawn from a population with known population standard deviation. So I have a known population standard deviation. This 1.2, that says sigma equals 1.2. And that means I want to use the z interval. So because I have a sigma, not an s, I have a population standard deviation instead of a sample standard deviation, I use the z interval instead of the t interval. So here I'm going to do a z interval here. So let's go see, sometimes we get a little bit different options. Well, I don't know what happened there. There we go. I go to stat, test, z interval is option 7, so I just get the 7. Stat. Now sigma, that was 1.2. That was, so over here, that was the 1.2 we were given. X bar, sample mean is 18. And let's see, sample size 40. And we want to build a 90% confidence interval, that's 0.9. So it's sigma x bar n, sigma x bar n, and then our confidence level. Sigma is 1.2, x bar is 18, n is 40, confidence level 0.9. You put those together, go down to calculate, and it spits out 17.688 to 18.312. 17.688 less than mu, and I'm getting 18.312. So short and sweet. Or I could use the formula here, but now this TC, maybe I'll write down my margin of error formula if you want to go that route. So the margin of error, it would be the critical value, but now it's a z critical value, multiplied by sigma over square root n. In our case, that would be the ZC. We're looking for a, I forget what the percentage was, 90%. So with the z, if you go to the z table, I think it's the second page in this one, but it's going to vary from table to table, where you look, and what's going to happen here, that down the bottom, I have sort of these critical values. So this looks a little bit different, but I'm looking for 90%. So I'm looking for 90%. It's just 1.645. So this just spits this out. I don't have to have that degrees of freedom, because it's the same for all n. Here. So what I'm going to get is 1.645. So this is 1.645 times 1.2 over square root of 40. You could calculate that out and build your interval that way, going 18 here. So you should really get, this should be about 0.312, because 18 plus that's 0.312. 18 minus 0.312 would give me 17.688. And so what I should get, let's verify that, 1.645 times 1.2 divided by square root of 40. I get 0.312. This is about the 0.312. So you could build this that way as well. Okay, 95% confidence interval, you would replace the 1.645. You go to the table with 1.96. So everything would look very similar. Or I'm just going to go use z interval again. Stat test z interval. And I just change my confidence level to 0.95. And go to calculate. Now I should still copy sort of this down. So I have z interval. Here I have sigma is 1.2, I have x bar is 18, I have n is still 40, but now my c level, confidence level, is 0.95. So I do that, and I get a slightly different interval. Now because I have a higher level of confidence, I'm going to be more confident in the interval, I have to make the interval a little bit bigger. So I expect the right-hand side to be bigger than 18.312, left-hand side to be less than 17.688. So I get 17.628. So that dropped down 0.06 in between there, and 18.372 went up 0.06, balanced on the right. So I didn't know the 0.06 without doing the calculation, but I could guess that it should sort of get bigger that way. Okay. Next guy, this says a sample of size 10 is drawn from a normal distribution. Sample has mean 24 and standard deviation 3.4. So one thing that's going on here is this is a small sample, so I have to be worried about will the central limit theorem hold? Will my sampling distribution be a normal distribution? But because I'm drawing from a normal distribution, it does not matter what the sample size is here. So all our steps here are legitimate. So 99% confidence interval. Because the standard deviation comes from the sample, I'm going to do a t interval. And I never remember exactly what shows up here, so that's going to be option 8. So it's x bar sx n. So it's x bar sx n. The t interval and the z interval have things in slightly different orders for whatever reason. X bar, the mean is 24. Sample standard deviation is 3.4. Sample size is 10. Confidence level is 0.99. So you put that together, or you just sort of use the margin of error formula we're working on. Let's get this over. Mean is 24. Standard deviation is 3.4. Sample size 10. Looking for a 0.99, 99% confidence interval. And we calculate, and we get 20.506 to 27.494. So 20.506 less than mu, less than 27.494. So there we go. This should be centered around the mean, which is 24. That seems about right. Next one, same thing, but now we have a 90% level of confidence. So again, we use t-interval. Here, x bar is 24. Sx is 3.4. I guess I'm writing equals instead of colons now. N is 10. Confidence level, this changes to 0.9. So I have a lower level of confidence. That should actually shrink my confidence interval. So I can be sort of wrong more often, so I can get sort of a smaller target here. And so now to do this, I'm going to go, whoops, not second. Stat test 8 is the t-interval. And I've got everything already there. I just changed the 0.99 to the 0.9. I'd enter in this data for the statistics. I should get a smaller interval, 22.029, get closer to the middle. This 27.494 should go down to 25.971. So I have 22.029 less than mu less than 25.971. So there we go. Next one. Okay, so it says a bag contains a large number of red and blue marbles. Pull a sample of 40 marbles from the bag. In the sample, 23 of the marbles are red and 17 are blue. Now we're going to find a 90% confidence interval for the percentage of red marbles in the original bag. So there is a formula you can use to find the margin of error here. What I'm going to do instead, this is a proportion problem. I'm going to go through to stat, test. I'm looking for an interval, and it's going to be a 1 proportion z interval. So we have really 1 proportion here because it's really what we have. We have red marbles. We have 23 out of 40 of the marbles were red. So what I'm going to do is, this is just x, so let me write this down. 1 prop z, because there's sort of a standard normal distribution beneath this, so that's a z. And I just put in x, I put in n, and I put in my c level. So x is either a 23 red, 40 overall, and my confidence level is 0.9. So you put that in, you just do 23 out of 40. Confidence level is 0.9 from the last problem. And I get 0.44643. And this is sort of the true proportion of red. It's between that and 0.70357. So this isn't terribly helpful here, because what we're saying is we think the percentage of red in the bag is somewhere between like 45% and 70%. It's a fairly big range still, but maybe narrowed it down some. Now for blue, we do the same thing, but instead of 23, we get 17. So we're going to do the 1 proportion z interval. Now this x changes to 17, and it's 40. Confidence level is 0.9 still. And so what I need to do is, let's see, stat, test, forget what number it was. If it was like 9 or 0, I can just hit that number and go down there without having to scroll through, but it's actually A on this calculator anyway. So you change the 23 to a 17. Go to calculate. I get something a little bit different here. Note I've still got that wide range, but it's 0.29643. Less than p less than 0.55357. So that's really what I would do. If you wanted to build this up using sort of the formulas in the book sort of by hand here, what I would do is your margin of error here, again, it's a critical value, so in this case it would be z, well, we'll just put a c, so 0.9 in this case. And what I'm going to get is multiplied by some kind of a standard error here. In the case of these proportions, this is square root of p times q over n. So the 0.9 critical value, that's the 1.645. I get a square root. The p, really, that's going to be the 17 out of 40 in this case. The q is going to be sort of the 1 minus that, or 23 out of 40, and then I divide by 40. So you can calculate this all out. And let's see, we've got about, let's see, 55, 29, about 26. This should be about 0.13 here if you calculated that out. Let's see if that actually checks out. Times square root, so we have 17 divided by 40 times 23 divided by 40 divided by another 40. Well, it turns out I don't need parentheses here, but you might be smart using them on the fractions if you're not comfortable with that. And I get like 0.1286 here, 0.1286. So I said something like 0.3, but I'm sort of eyeballing it, so it's about that. Okay, next one, find an 80% confidence interval for the percentage of red marbles in the bag. Note we did red, then blue, then red. It's probably a bad setup here. But then we're going to do 80% for the percentage of blue marbles in the bag. So what I'm going to do, I'm going to do the blue one first because I just did that here. So this is going to be 1 prop z interval. X, the blue was 17, n was 40, and we're just changing our confidence level to be a little bit lower. That should shrink our confidence interval down. So what we had was 0.29643 for the blue to 0.55357. We should shrink that down a bit where both of these numbers get sort of closer together. So let's see what happens. Stat tests. Go from the bottom this time. That probably didn't help a whole lot, if at all. And all I'm going to do is change my confidence level to 0.8. Go to calculate, and I get 0.32. Didn't look at that long enough. 0.32483. True proportion looks like it's between that and 52517. 0.52517. So what I got, 32483, 52517. A little bit bigger here, a little bit smaller there. The other one, so this is then going to be 80% confidence interval. For the red, this is a 1 prop z interval. X is 23, n is 40, C level is 0.8. And so I'm going to do stat test. Oops, too many. There we go. And I just changed that 17 to 123. Go to calculate, and I get 0.47483. Less than P, less than 0.67517. So there's my answer. Okay, next question. Here. So this is a sample of size 30 is taken from some kind of probability distribution. A 90% confidence interval for the population mean is calculated to be 51.518. Less than mu is less than 56.482. Which of the following could be a 95% confidence interval for the population mean? So this is our 90% confidence interval. We're going to build a 95% confidence interval. So this is where we have to think about, should my interval shrink, get smaller, get bigger, what's going on here? So if I do a 90% confidence interval, what's going to happen here is I want to think about 95%. I need to get more of the time in that range. And so that means I sort of have to have a bigger target. Let's change that up. So if I want to be sort of correct more of the time, I'm going to hit sort of this target 90% of the time. So to get 95, I've got to get a bigger target. And really, I sort of get the 2.5% on each side. So not a whole lot bigger, but some bigger. So what has to happen here is this 51.518 has to shrink some, go down a little bit smaller, and the 56.482 has to get a little bit bigger. So let's see here. 51.518, let's see. These two, the 51.518, actually got bigger. So those two, certainly not correct answers here. Now at this point, I mean, got a 50-50 shot guessing, but let's look at the bigger one, 56.482. That should get bigger. So we went smaller on the left, get smaller, bigger on the right. 56.482, they both got bigger here. So we can't really tell directly from that comparison here. What we can do, we can see how much they got bigger. So what we're going to do, let's see here. So if I do 51.518 minus 51.013, so let's actually say this is 51.518. This is 56.482. And then we've got two potential intervals. So let's take just a different color. So let's do this red one. Here, let's say that's the first one, 51.013. And 56.987. And so the amount that this grew by, let's see, 56.987 minus 56.482, the amount that grows by is 0.505. So this distance here is 0.505. Now that should match over here. You can do the subtraction and check. 51.518 minus 51.013, and we get 0.505. So those match. Now that means that's still in contention. Maybe the other one matches as well. So the other one, let's maybe do this in green. This one actually gets a bit bigger yet. Here, so what I get is the 50.633 and the 59.367. So we've got sort of these cutoffs here. This distance here is, move that over, 51.518 2.518 minus 50.633. So what we get is 0.885. So this is 0.885. And the question is, do I get the same distance here? And when I look at that, it looks like probably not. 59.367. And I subtract off 56. Yeah, that's more than 1, certainly 0.482. So I get sort of a 2.878. So I get sort of not a symmetric growth on both ends, which it has to be if I just increased the percentage of the level of confidence. So I can't do this green one, so that one's not correct. And so my answer should be A here. Now, it turns out you can actually figure out what this should be here. So if I look at this, this is a little more advanced here, but my margin of error formula, this should be generally, let's see, do we know is a sample? So it doesn't really say anything about like sample standard deviation or, well, sample standard deviation or population standard deviation. So I don't know if we're using a Z or a T. Let's assume we had a population standard deviation using a Z just because it makes the critical values simpler. So what you could do here, is you could say that I have ZC, the margin of error is ZC times times sigma, which we don't know what sigma is, over square root of n. We know that's square root of 30 here. So for the blue, what you get is ZC, our critical value for 90%. We go here, 90%. That's 1.645. So again, we're going to assume that this is normal. Maybe it's a T here. So we can do this here. The margin of error, I can actually figure out what that is. So what I can do is I can take the distance between the two endpoints, 56.482, subtract off 51.518, and then divide that by 2. So the idea is I should have mu in the middle, or not mu, but x bar, and this should be x bar plus e, and this should be x bar minus e. So the total distance between these should be 2e. 1 e to get up to x bar, another e to get from x bar to the right endpoint. So sort of what I do is I subtract them and get 2. That's 2.482. So I know this e here. I can get rid of that and get 2.482. And now I can solve for sigma. So sigma is 2.482 times square root of 30 over 1.645. And so that should be 2.482 times square root of 30 divided by 1.645, something like 8.26. So that's sigma if we're using a Z distribution. And that means for a 95% confidence interval, our margin of error for this red guy, margin of error should be, let's see, 56.987 minus 51.013. Whoops, well, divided by 2, so I'll hit enter and then divide by 2. 2.987, so I expect to get 2.987 equals, now our new critical value, not 1.645, for 95%, it's 1.96 here. So 1.96 times sigma, no, we know sigma now, 8.26 over square root of 30. So the question is, does this actually work out? Whoops. So I get 1.96 times 8.26 divided by square root of 30. Hope is I get 2.9. There's a little bit of error there. Maybe this was with a T distribution. But you can see sort of this works out okay. So we have to think, is this a T or a Z? But you get kind of a rough sense here of how you would go about this. It's also possible I created this question without being completely precise, but I think this was, maybe it's from a T distribution, which would give us different numbers here and here, slightly different ratio, but we're kind of in the ballpark there. Also, I guess we rounded the 8.26. Actually, let's see how much difference that makes here. So if we don't round that 8.2, so if you did 1.96 times 2.482, so this thing here instead of 8.26, times square root of 30 divided by square root of 30. So let's actually work this out here before we do that. So this is 1.96 divided by square root of 30, and then the 8.26 is 2.482 times square root of 30 over 1.645. The square root of 30 is actually cancel. And what I get, 1.96 times 2.482 divided by 1.645. Here that gives me 2.95. I'm still a little bit off. Maybe it was a t thing, but kind of close. Okay, next one. Sample size 50 is taken from a probability distribution. A 90% confidence interval for the population mean is shown above the number line. So I'm going to say this thing here, that's our 90% confidence interval. Below the number line are dashed intervals, so we want to circle the dashed interval that could be a 60% confidence interval. So this is supposed to be a number line, probably isn't actually helping here. So what I want to think about here is I have a 90% confidence interval. If I get a lower level of confidence, what's going to happen in the interval? So it should be symmetric around the same point here. So it's either going to be this top one dashed, so maybe circle that in orange here, or how about in blue, this smaller one. So the question is, should my confidence interval get bigger or smaller when I go from 90% to 60%? So the idea here is, I'm going to think about like I'm shooting at a target here. This one I'm hitting 90% of the time. If I only need to hit 60% of the time, I can actually have a smaller target. If I have a bigger target, I'll hit it a higher percentage of time. Smaller target, less percentage of time. So really my answer here is this smaller dashed one, sort of the third from the top, or maybe second from the bottom. Next one. Okay. Now we got a series of questions here about when we should use a normal distribution or a t-distribution, or we really can't use either. So again, I'll say if you're using a different book, you might get slightly different explanations for these. I'm going to argue the ones I do are actually sort of more correct here than a lot of them, but sometimes you're really splitting hairs about the confidence interval difference isn't really that different, is very small between a t and a z anyway. Okay, so this one anyway, it says a sample size 20 is drawn from a normal distribution. So when I draw from a normal distribution, I don't care about this sample size. So it's a small sample, which we're going to define as less than 30. But because I'm drawing from a normal distribution, the central limit theorem works, and everything's going to be sort of okay. It's going to be either a z or a t. Sample mean is 78. I don't really care about that. But I have a sample standard deviation here. So what I have is a sample standard deviation. I don't know the population standard deviation. What distribution should be used in order to build a more accurate 90% confidence interval for the population mean? Because of the sample standard deviation, and I don't know the population standard deviation, I'm going to do B. I'm going to use my t distribution. Okay, next one says sample size 20 is drawn from a normal distribution with a known population standard deviation of 12.3. Sample mean is 78. What distribution should be used in order to build a more accurate 90% confidence interval? So if we know the population standard deviation, that's when we use the norm. Again, we're drawing from a normal distribution, so we can get away with a small sample size. Sort of an interesting variation here. I'm not sure if there's one like this, but if I knew both the population standard deviation and the sample standard deviation, what I ought to do is use the normal distribution with the population standard deviation. So the goal of the sample standard deviation is to estimate the population standard deviation. But if you have the population standard deviation already, you might as well ignore the sample standard deviation. Okay, next one. So a sample of size 40 is drawn from a normal distribution. So big sample size. So it doesn't actually have to be from a normal distribution here. Sample mean is 78. Sample standard deviation here is 12.3. And we want to build a 90% confidence interval. Because we have a sample standard deviation and not a population standard deviation, answer is B. We use a t distribution. Next one. So the sample size 40, again big, so I don't care if my distribution is normal or not. Now I have known population standard deviation 12.3, and sample mean, I don't really care what the sample mean is. Distributions we use to build a certain confidence interval for the population mean. Known population standard deviation, that's a sigma, so we're going to use the normal distribution. Next one. It says a sample of size 10. Okay, 10, that's small, is drawn from a distribution that we don't know is normal. Now at this point, the central limit theorem doesn't apply. It means the x bars, the sampling distribution, aren't necessarily a normal distribution. All of our calculations break down here. So I don't even care what the rest of this says. This just isn't going to work. So I'm going to do neither distribution is appropriate here. So once I have a small sample size, so small, and I have sort of the non-normal distribution here, then this won't work. if either the sample size was big or it was drawing from a normal distribution, then I'd have to pay attention to the rest. And I have a sample standard deviation, so it would have been the t, but neither one works. Next bit. So the sample of size 10 is drawn from a distribution that is not normal. Again, small sample size, not normal. I can stop here and say neither one works. In this case, you have a population standard deviation, so it would have been the normal distribution if either of these two things didn't sort of get in my way, but neither one will work. Next one. Sample size 40, that's big, is drawn from a distribution that is not normal. So non-normal, but big enough that the central limit theorem is going to tell us our sampling distribution is essentially a normal distribution. So our sample has a sample mean, 78, and sample standard deviation, 12.3. So everything works, and we have a sample standard deviation. That means we're going to use the t distribution. Okay, last one here. Let me show the previous one with it. So the sample of size 40, again, big enough, drawn from a distribution that is not normal. So big enough means this is going to work out. The distribution has known population standard deviation. So population standard deviation, that means we have a z distribution or the normal. So that's our last one, and we are done here.